horizontal distribution of air pressure on the Earth's surface is shown by means of isobars. Isobars are lines drawn through points of equal pressure. They are drawn at pressure intervals of either 3, 4 or 5 millibars. Factors which control the distribution of temperature on the Earth's surface equally govern the distribution of the pressure as well. This is mainly due to the fact that there is a close relationship between pressure and temperature. Since there is a great variation in the amount of insolation received at different parts of the Earth's surface, there is a corresponding variation in the temperatures also. After going through this lesson, you would be able to understand the distribution pattern on rotating and homogeneous Earth, to understand the seasonal variations and the pressure patterns. When we add the effect of Earth's rotation to temperature, the Coriolis force comes into picture. Some of the air rising near the equator and moving towards the poles in the upper atmosphere is turned aside by Earth's rotation or by dynamic processes. The result is that not all air rising from the equator goes to the poles. Some of it settles down in the cells in the subtropical regions. These subsiding air currents create subtropical high pressure cells between 25° and 35° north and south latitudes. There are two factors which are believed to contribute to the general subsidence found here. First, when the rising air currents move away from the equatorial region, the release of the latent heat of condensation keeps them warm and beyond. But radiational cooling results in their increased density in the upper atmosphere. This accounts for the subsidence of cold and dense air in the subtropical regions. Secondly, with the increasing distance from the equator, the Coriolis force gets stronger so that the poleward moving winds are deflected into a nearly west to east flow as they get near 25° north and south latitude. Thus, the Coriolis force produces a blocking effect causing convergence aloft. This results in general subsidence between 25 and 35° of the latitude. Subsiding air currents are relatively drier. The weather in this zone remains fair and dry. Besides, relative humidity of the descending air currents is further reduced by the effect of adiabatic heating. This accounts for the fact that all the hot deserts in the world are situated in the subtropical high pressure belts. Poleward of the subtropical high pressure cells in both the hemispheres are large belts of low pressure at about 50 to 65° latitude. This is called a subpolar low pressure belt. Here, the westerlies and the polar easterlies meet to form a convergent zone. This region where the cold polar winds and the warmer west winds clash is called as the polar front. Temperature does not account for the existence of the low pressure belt, which is perhaps produced by the dynamic factors involved with the rotation of the Earth. In the polar regions, there are polar highs caused by extremely low temperatures and subsiding air. From the preceding discussion of the distribution pattern of the surface pressure on the rotating Earth with uniform surface, it emerges that there are in all 7 alternating low and high pressure belts on the Earth's surface. Equatorial trough of the low pressure, subtropical high pressure belt in the northern hemisphere, subtropical high pressure belt in the southern hemisphere, subpolar low pressure belt in the northern hemisphere, subpolar low pressure belt in the southern hemisphere, polar high northern hemisphere and polar high in the southern hemisphere. The arrangement of the continuous pressure belts around the Earth as referred to above would be ideal as well as hypothetical and far away from the actual conditions as they are observed on the Earth's surface. In fact, the unequal distribution of the continents and the oceans makes the distribution pattern more complicated. The annual average sea level pressure is represented in the figure. We find that because of the preponderance of land masses in the northern hemisphere, the idealized zonal pattern of surface pressure is disrupted. The so-called pressure belts are broken into cells of high and low pressures which are elongated in shape and extend in east-west direction. On the contrary, the southern hemisphere is preeminently a water hemisphere, and there is progressive diminution of the land masses in higher latitudes. The only true zonal distribution of pressure exists in the region of the subpolar low in southern hemisphere where the ocean is continuous. The annual average sea level pressure pattern as represented in the figure brings out the following salient features into sharp focus. There is a trough of low pressure in the vicinity of the equator, which is to a certain extent zonal in character. The subtropical regions in either hemisphere are dominated by a number of discontinuous high pressure cells called the subtropical highs. These highs are definitely not of thermal origin. They are supposed to be induced by mechanical or dynamic means. Poleward from the subtropical highs, there is a decrease of pressure towards the subpolar lows located in the vicinity of the Arctic and Antarctic circles. In the northern hemisphere, the subpolar trough of low pressure consists of individual cells of low pressure over the oceans. Contrary to this, there is a continuous belt of low pressure at about the latitude of Antarctic circle. The subpolar lows owe their origin to the dynamic rather than thermal causes. The polar areas in either hemisphere are dominated by anticyclones that are of thermal origin. We have noted earlier that there are 7 alternating belts of low and high pressures on the Earth's surface. Here, for the sake of convenience, each pressure belt has been described in detail. Equatorial trough of low pressure. The equatorial trough of the low pressure is located in the vicinity of the geographical equator between the latitudes 50° north and 50° south. This is the mean position of the pressure belt. In fact, like the belt of the maximum temperature, this trough of low pressure extends more to the north than to the south of the equator. Width of the equatorial trough is not uniform in different parts of the equatorial region. The average pressure in this belt is less than 1013 millibars throughout. But in the eastern hemisphere, it is generally less than 1009 millibars. Since the maximum insolation is available in the equatorial region, the Earth's surface is intensely heated during the day so that the lowermost layers of the air get warmed. The heated air expands, becomes lighter and rises upward. Thus, convectional currents are set up in the atmosphere throughout the year. Because of the warm and moist air moving upward, it has great potential for tremendous amount of energy in the form of latent heat of condensation. In the equatorial low pressure belt, the air is warm and moist. Equatorial trough of the low pressure is a zone of convergence of trade winds blowing equatorward from the subtropical belts of the high pressure in the northern and southern hemispheres. This belt is quite distinct on the map, showing the distribution of the mean annual pressure for the world and average distribution of the pressure for January. But on the pressure distribution map of July, the equatorial trough of the low pressure appears to be highly irregular and indistinct. In July, it connects the low pressure areas situated in the warmer regions of the southwestern parts of North America and the hot interiors of the Southwest Asia. In July, it is positioned north of the equator. The equatorial trough of the low pressure is, as it were, tied with the sun. Therefore, it shifts towards the north and south of the equator with the apparent movement of the sun. During the month of July, this low pressure belt extends up to latitude 20° in the North Africa and to north of Tropic of Cancer in the vast continent of Asia. In January, it migrates to the summer of the southern hemisphere. It extends to the latitudes of 10° and 20° south. In this belt, the temperature is high throughout the year, so the air pressure is always low. Thus, the equatorial low pressure belt is thermally produced. Here, the pressure is more uniform than in other parts of the world. In this belt, the diurnal variation of the pressure is a distinctive feature and is more pronounced. Subtropical high pressure belt. The areas of the subtropical high pressure are located between the latitudes 25° and 35° north and south. The most important feature of this pressure belt is that it is broken into a number of high pressure centers or cells. These high pressure cells or centers of action are the key points of the distributional pattern of air pressure over the globe. But the exact causes of their origin are not yet fully known. The meteorologists agree that these subtropical high pressure cells are dynamically produced due to the rotation of the Earth. The subtropical highs are areas of sinking and settling air from higher altitudes which tend to build up atmospheric pressure. In the upper atmosphere over the belt, the upper level westerlies and the antitrades converge and set up descending currents in the atmosphere. These high pressure areas have no prevailing winds. The winds are light and variable. There are occasional calms. However, sometimes these belts are invaded by extratropical or tropical disturbances attended by stormy winds. Because of the subsidence of the air in these areas, the weather for most part of the year remains fair and dry. Subsidence also causes an increase in the temperature of the surface air. All the hot deserts of the world lie in this belt and are located on the western margins of the continents. These high pressure zones are called the horse latitudes. The cells of high pressure persist throughout the year over the large ocean basin where there is a slight seasonal change in their position. However, there are marked variations in their intensity and size. In the southern hemisphere, higher pressures are observed during the winter seasons. In this hemisphere, there is an almost continuous belt of high pressure because the high pressure cells spread to adjacent continental areas during the winter season. In the northern hemisphere, during the warmer part of the year, the subtropical high pressure areas record higher pressures and become larger in area. Even though they are connected with continental highs at higher latitudes by ridges of high pressure, the continuity of the belt is not maintained. The daily weather charts do not confirm this semi-permanent character of the subtropical high pressure belts because of frequent variations in their size, location and intensity. The subsiding air currents produce stability in the atmosphere and also create dry air masses. Rainfall is extremely limited in the areas under the influence of high pressure cells. Another characteristic feature of subtropical highs is that they extend to about 9,600 meters above the mean sea level. As discussed earlier, most of the subtropical anticyclones are asymmetrical in their internal structure. In close proximity to the Earth's surface, the center of highest pressure is located over the eastern part of the oceans, while at greater elevations the same is located farther to the west. Subpolar low pressure belts. In the southern hemisphere, there is an uninterrupted belt of low pressure between the latitudes 60 degree and 70 degree, where there is a vast expanse of oceans. But in the northern hemisphere, there are large land masses between these latitudes which are very cold. Therefore, the pressures over these land masses are increased. Thus, the continuity of the subpolar low pressure belt in the northern hemisphere is broken. However, there are well-defined low pressure cells over the northern oceans. The centers of these low pressure systems lie in the vicinity of the Aleutian Islands in the Pacific Ocean and between the Greenland and Iceland in the Atlantic. During the winter season, there is a great contrast between the temperatures of continents and adjacent oceans. This helps in reinforcing the Aleutian low and Icelandic low. In summer, the temperature contrast between the continents and oceans is much reduced so that the belt of subpolar low is more developed and becomes more regular. Polar highs. Pressures at the poles are consistently high throughout the year. In the northern hemisphere, the high pressure area is not centered at the pole, but it is believed to extend from the northern Greenland westward across the islands situated in the northern part of Canada. From the reports of explorers of Antarctica, the existence of relatively higher pressure near the South Pole is confirmed. As regards the origin of the cap of high pressure at the poles, thermal factor seems to be more important than the dynamic factor. Although, because of the diurnal rotation of the Earth, the layers of air at the poles are thinned out. The persistent low temperature makes the polar air cold and heavy. This gives rise to the caps of high pressure in polar regions. The prevailing easterly winds blow out of these caps of high pressure to the subpolar low pressure systems. In the northern hemisphere, these easterly winds are deflected to the right of their original path and become polar northeasterlies, while in the southern hemisphere, the polar winds blow as southeasterlies. It may be pointed out that the extreme cold of polar regions makes the work of collection of atmospheric data very difficult. Thus, the paucity of accurate climatic data about these regions stands in the way of describing the climatic conditions of these extremities with far degree of accuracy. The sun's direct rays change the positions as they migrate between the tropics of Cancer and Capricorn. Thus, following the apparent movement of the sun, the pressure belts move northward in July and southward in January. These seasonal variations in the pressure pattern are of course thermally induced. In the tropical region, seasonal variations in the pressure are no doubt very small because temperatures remain uniformly high throughout the year with little variation. In high latitudes, on the contrary, the seasonal variation in the pressure tend to be more larger because of an increasing contrast in the angle of incidence and the length of daylight. The general pattern of seasonal pressure variation is changed to a great extent in the northern hemisphere, where there is preponderance of land masses over the oceanic areas, accounting for about 40% of the total surface. Salient features of the pressure distribution in January, as illustrated in the figure, are described in the subsequent paragraphs. Because of the apparent movement of the sun towards the Tropic of Capricorn, the equatorial trough of low pressure is displaced well to the south of the equator. This shifting of the low pressure belt is well marked over the warm continents of the southern hemisphere. January being one of the summer months in the southern hemisphere, the continents of Australia, Africa, South America are relatively warmer and there are distinct low pressure cells over them. The subtropical belt of the high pressure in the northern hemisphere is located well to the north, especially over the cold continents. In fact, the isolated cells of high pressure are united to form a continuous belt. The high pressure cells over the Pacific and Atlantic Oceans become weaker in the summer. High pressure exists over the North America and Eurasia. In the northern hemisphere, the northeastern part of the Siberia and Asia becomes the coldest region on the Earth's surface with highest temperatures. During the summer of the southern hemisphere, the subtropical high pressure belt lies at latitudes 30 degree and 40 degree south, with centers of the Pacific, Atlantic and Indian Oceans. In the northern hemisphere, because of the large continental areas, the subpolar low pressure belt is represented by individual oceanic cells and their continuity is broken. There are two low pressure cells found over the North Atlantic and the North Pacific Oceans and are known as the Icelandic low and Aleutian low respectively. In the southern hemisphere, since there are no land masses in the high latitudes, there is well developed circumpolar belt of low pressure. The air pressures observed over the coastal regions of the Antarctica and the southern oceans clearly indicate that beyond latitude 65 degrees south, there is gradual increase in the atmospheric pressure. The southeasterly winds from the continental land masses of Antarctica confirm the above assumption. In the east central part of very extensive and deep high pressure cell is established. North America being smaller in size than the vast landmass of Eurasia, the high pressure cell over there is not so well developed. This is the period of summer in northern hemisphere. Because of the apparent movement of sun towards the Tropic of Cancer, all the pressure belts shift towards the north. Therefore, equatorial trough of the low pressure also is located well to the north of the equator, especially over the warm land areas of the northern hemisphere. The heat lows are conspicuous over the southwestern United States and over India, Asia Minor and northern Africa too. In northern hemisphere, the well-developed high pressure cells are found over North Atlantic, North Pacific. The Pacific High and the Azores Bermuda High are noteworthy. In July, there is winter in the southern hemisphere. The subtropical high pressure belt is more continuous than in the month of January. There is a high pressure cell established over the continent of Australia. However, in the southern hemisphere, the high pressure develops only slightly on the continents, for there are no large land areas in the high latitudes. Like January, in July too, The subpolar low pressure belt is rather continuous in the southern hemisphere. But in the northern hemisphere, the subpolar and the equatorial low pressure belts merge over the continents. However, the subpolar low pressure belt persists to a small degree over the oceans. In this lesson, we've learnt about how sun and pressure belts are interrelated, and we've spoken about the 7 different pressure belts and also understood the distribution of pressure belts in January and July month.